Yes, well, thank you for this opportunity to talk to you today about Waratah Seed. I'm, of course, not the only one who will be doing so. It's also Dat Tran from UNSW will be talking. And we did expect to have Taufik Hook from Spiral Blue talking as well. But unfortunately, Taufik's mother is in hospital on an emergency basis, and so he just cannot be here tonight. And so in some ways, we're scrambling in that I was intending to only give a 10-minute spiel about Waratah Seed and then give over to Dat and to Taufik to talk. So instead, I'm going to give a 10 to 20-minute intro. Then Dat will talk for of order 20 minutes. And then I will come back at the end to talk about the other payloads on Waratah Seed. So what's Waratah Seed? It's basically Australia's first industry rideshare satellite where we take payloads that people pay us the privilege for. We take the payloads, we help integrate them into the spacecraft system. We then launch the spacecraft and operate it in space and enable people to get their data so as to have space heritage and thereby be able to either do the science/services that they want to do, but also to be able to then sell their technology and or their services to others. So Waratah Seed, we'll talk about the origin of that in a moment. We see here the Waratah Seed satellite on the right as you look at it, and Kuava 2 on the left. These are 6-unit CubeSats. So they're 30 centimeters tall by 20 centimeters wide by 10 centimeters thick. Essentially the size of two Coles or Woolworths, assuming I'm allowed to use those words at the moment, but two loaves of bread. Of course, they're a lot heavier. These are 7 or 8 kilograms, whereas a loaf of bread from Coles or Woolworths is perhaps 1 kilo, might be a half kilo. This is not something that's done just by me or the University of Sydney. You can see the members of the consortium here at the bottom. At the University of Sydney and Kuava. Well, Kuava stands for CubeSats for the sea, UAV for uncrewed aerial vehicles, and then A for applications. So Australian Research Council Training Centre, which ended at the end of 2024. AXA is the Australian Centre for Space Engineering Research, run by Andrew Dempster at UNSW, Macquarie Uni, UTS, Delta V New Space Alliance, gone through various names, and we'll come to that in a moment, and then Sabre Astronautics, where many of you will know of at least Jason Held, who's the co-founder of that. You can see the logo for Waratah Seed here, at least the old one. There's a YouTube video that you can go and look at. And New South Wales Government and SmartSat CRC are here because New South Wales Government gave a substantial amount of the initial funding, about $500,000, and SmartSat CRC helped to give of order 400K. Okay, so why do we have Waratah Seed as the name? Where does it come from? You can see here the logo. Yes, you can't see my cursor. Waratah Seed here. You can see the Waratah flower, the spacecraft here, and then the flowers of the stars that we're in space with. Grace Brown, Tom, is a Wood and Jerry artist. She created this. And where does the name Waratah come from? It's actually an Eora word, meaning seen from afar or beautiful. Both, of course, appropriate names for a spacecraft up in space. And it's worth mentioning that Waratah is a New South Wales state flower, but they grow across Australia. And seed, well, we wanted a strong and vibrant New South Wales, and for that matter, Australian space sector to come from Waratah Seed. And I, as the leader of this consortium applying for New South Wales government funding, thought, well, how can they possibly not fund us if we call ourselves Waratah and Seed, Waratah Seed? It just shows the importance of having a good name often. I think there were other reasons we got chosen as well, but it doesn't hurt to start off with a good name. So Waratah Seed is really intended to go from the left-hand side, the beautiful deserts of Australia, to something which is a world-leading position in space research. Waratah Seed last year won the Small Satellite Mission of the Year award from the SmallSat Conference in Utah and the American Institute for Astronautics and Aeronautics. And so it's all about helping our space sector grow and become world competitive. And just to go on about this a little bit, on the left-hand side here, you can see the finalists for the SmallSat Mission of the Year. If you count them, there's 5 which relate to NASA. There are 2 which are arguably ESA missions, and we beat them all. And you can see here on the right, our chief engineer, Shilian Bai, our former postdoc, Yung Ho Un, and then one of our clients, Peter Toth, the principal of extraterrestrial power that you'll hear about later. And the lady here is the vice president of the conference. Now, I knew you would want to hear something about a launch. Oh. And here, now. Yeah, excellent. Was that me or you?
Falcon 9 is unstarted. LD is go for launch.
Stop it for a moment. We unfortunately didn't manage to practice this beforehand. So, Alia, you may know what to do. So I don't have it on at the moment, but let's put it back.
10, 9, 8.
Go. It could be just the buffering. This is a rather large file. It's something like 100.
LD is go for launch.
So look, let's just let it go, and occasionally you're going to get a burst together, and it's all about our
ignition. And we're done with Falcon 9. Go Transporter 11.
SpaceX rocket, Transporter 11, and 3 into space.
And we'll be standard.
Here it's all about exceeding expectations. Don't worry about the sound. And we'll just let people read the words there and look at the side. I think that is it. So I'm sorry that that wasn't as sexy as it was intended to be, but we'll try playing that tutorial later. So let's see whether that works again. We're just going to do it. Okay, so the outline. We've done the introduction. I'm going to talk next about what Waratah Seed involves and why. Very little bit about its genesis. I'll then talk about very little bit about the payloads and process. That will involve another video, which has no sound, I'm pleased to say. Then talk a little bit about the satellite, and then we'll talk about the UNSW payload, Harry. Then we'll talk about results from the other payloads, current status, some of the wider implications, and then talk about one future path, which involves taking Waratah Seed and extending it into a pipeline to space with multiple missions so that we have a regular cadence that people can plan on and actually get their technology into space to get heritage and to actually operate it there and do services for Australia and other groups. So that's the plan. And I mentioned already that Spiral Blue and Taufik Hook aren't able to be here today because of a medical emergency. Should say that his mother is now out of danger, so don't worry. So what is Waratah Seed and why do we do it this way? It's the pilot space qualification mission or project of New South Wales's space industry development strategy, something developed by the Berejiklian government. It's basically an industry rideshare satellite, 6-unit CubeSat, which I'll explain in a moment. So that means we're taking payloads from industry and academia for money, and we're then implementing them and getting them to space. So that instead of everybody having to create their own satellite, they pay us instead to help actually get them to space at a much, much lower cost than having to do their own satellite. Standard number for a 6U CubeSat, at least in Australia for us, about 1.5 million Australian dollars. So would you like to spend that, or would you like to spend, a sixth of that and get to space much more quickly and without having to create a satellite, which, is outside the skill set for most people. So Koala's bus, it's mostly COTS, and then the payloads are coming from industry. Many foci, basically developing space heritage for companies and other client payload providers, and then training people, basically to try and grow the space sector, be part of it, and grow it. So multiple things there. So here's, it's looking great on, it's absolutely great on my screen.
Mine on the one here.
Okay, so it's just the one here. It's probably just a loose connection.
Space radio.
No. So as I said, this is a New South Wales pilot space qualification mission. Had something like $500,000 in the budget for us. In this case, after we won the proposal, and it's to try and give people low-cost access to space. So let's go on. Excellent, Alia. Okay, so what's a CubeSat? Basically, it's a satellite build-up of cubes, which are 10 centimeters on a side, and with less than 1.3 kilograms per U. Basic idea, the standard of this standard came in 1999, so it's now, 26, 27 years old. It's rather old. And of course, you can build up many different sizes of satellites this way. And why would you do it? Basically, it's all the power of standardization and of allowing people to do the parts of space that they want to do. It allows us as scientists or engineers or commercial people to focus on what we consider important and just regard the satellite as a tool and not our primary focus. And here the point is that most of us don't want to design our own computers or fridges or cars, etc. We buy them and we do the things that interest us most. So again, all about standardization, commercial off-the-shelf or COTS parts, and then trying to add things that make value for us. Many reasons for standardization, and I'm not going to go through them. This is very frustrating for you guys here in the room. Number one, you have me, but number two, you have a flickering screen.
Not affecting. It's not affecting.
It's not affecting everyone online. So the whole point about a 6U CubeSat is you have a certain volume, and you're going to say, let's say 1.5 U of that is spacecraft subsystems, and then 4.5 U is payloads. And in our case, 1.5 U of those payloads came from a competition, which I won't really talk about, and 3 U were intended to be from commercial clients. So the competition people paid much, much less to get into orbit than the commercial clients.
I can't get you out of my head.
The refresh rate problem.
I can't see any of the chat, so I'm relying upon others to look at that.
Okay. Tell them to wait to the end.
Tell them to ask questions.
Okay, sounds good. Okay, so Genesis, where did it come from? Basically, it's this cast of characters on the right-hand side. You see Andrew Dempster on the top left, Brian Lim, Jason Held on the bottom right, and then Tim Parsons in the bottom, and me with a ponytail on the left there. And basically, cafe meeting at the bottom of the MLC building. Which then led to, well, among other things, Waratah Seed. Also led to the QB50 satellites, including UNSW Eco and Inspire 2, which is mine, or at least the one that I led. And these are the third and fourth Australian-built satellites to ever get into space and work. Koowarta 1, first one for the ARC Training Center for CubeSats, UAVs, and applications. It's a 3-unit CubeSat. And then Koowarta 2 and Waratah Seed are both 6Us. So in this case, it's 10 years for us to get to a 6U CubeSat. Lots of funding, resilience, problems encountered, and evolution. We didn't start off to do industry rideshare satellites, but it was something that with the ARC Training Center made sense to evolve into, because the training center was all about trying to link academia and industry. So there are multiple phases for Waratah Seed. We had a payload competition. We had to attract commercial clients. And so many of you will laugh at the idea of us academics trying to get into this because it is so difficult. Payload development and testing, integration, launch, commissioning, and then operational. And really, most difficult one for many of us academics is number 2 here. Actually attracting and then landing, so to speak, the commercial clients. Payloads, we'll go over these more. We had 5 from our payload competition, including Spiral Blue here, doing edge computing, Dandelions, biomaterials, extraterrestrial power and Europa power as solar cells, one case advanced silicon, and the other case perovskite, so an organic material. Sorry, go back here. And then Sparrowspace was also biomaterials. And then we had commercial client payloads. We had the UNSW SmartSat 1, GPS reflectometry with Harry, which Dat will talk about. Then UTS and Mawson rovers with the thermal control payload called Matilda. And then 2 which came out of the ARC Training Center, including Deneb Space's electropermanent magnet orca, which I'll talk about a little bit. And then let's try and see how well we go with talking about the space systems. I'm going to skip right over the payloads and go to here. So this is the 6-unit CubeSat. Looks rather pretty on the outside, and the inside it's full. Being of Scottish extraction, I don't like to waste things. So space here is that we want to use it, that volume. So here we have the UTS payload here. Extraterrestrial power solar cells are on the outside. Sparrowspace is in here. GPS reflectometry payload. So Harry is right at the bottom. More solar cells on this outside portion. Then we had some of the spacecraft components in here. The radio, the power supply up here, the onboard computer in here, our S-band antenna on the outside, the attitude determination control system, which is giving us problems at the moment, the S-band radio, and then the EMAG was down in here, and so was the Eddy experiment as well, and various deployables. And then Spiral Blue, their edge computer was just in here, and some other bits and pieces, and Dandelions just in here. So packed together, this is crazy for many people. NASA will tend to have one main payload. Nothing else need matter. That's not the way we wanted to go. We wanted to have two or three main payloads, and then a number of other ones, which are all treated equivalently in terms of pro rata for power, data, etc. So what about some results from Waratah Seed? And this is where we're going to go over to DAT. Now let's see whether we can switch relatively painlessly here.
Awesome, thank you. So, good evening, everyone. I hope you have a pleasant evening, although the weather is not very pleasant. My name is Dax, and I'm currently a technical officer. I'm working under Andrew Dempster since the start of 2025. So, I'm a newcomer to the industry. And so, during my presentation, if I say anything wrong, please pardon me. And I'm today on behalf of AXA to talk a little bit about our payload, Harry, and what we have accomplished so far. So, first of all, let's begin with a little bit of history. As you know, AXA have a huge interest in and we have a long history of research about GNSS system. And for a while now, we have interest in navigation in space as well as reflectometry research. So the reflectometry is essentially we're trying to capture the reflect signal from the GNSS satellite down to the ocean and reflect back to our receiver. And we try to use that information to determine the ocean and the eye surface condition. The issue with this research is in order for us to analyze the data as all, the receiver need to have a certain attitude and either on the plane or ideally on the low Earth orbit satellite. That's why we want to put Harry into space. And this is the reason we developed Harry. So what is Harry? So Harry essentially consists of a two genetic receiver. We call it the Kia. So the Kia is a UNSCBU developed GPS L1 receiver. It's very old. It only have 2-bit RF front end and single channel with capability of 16 megasample per second. And we choose the Kiev because we know that it works and we have flew it in several space missions. One of them is the Echo 50 that Iver has shown you a couple of minutes ago. And the architecture is essentially the two Kiev. So we have the first one. Oh, by the way, and this is we have two systems. We're using the same Harry architecture on both of them, the Curva 2 mission and the Waratah Seed 1. And the overall structure is the same. We have two key receivers. The first one will on the Curva 2, we have the right-hand circular polarized antenna pointing upward to try to capture the direct signal. And the second one, we have the left-hand circular polarized antenna pointing downward to capture the reflect signal. Because you know, like in the mirror, when you point the light source into it, your reflect image will be like reverse. So we need a left-hand circular polarized antenna to capture it. And that is our first mission for the Curva. We try to get the reflectometry. Why on what is this? The mission focus on navigation. So we only have both of the keys. We have the same right-hand circular polarized antenna pointing roughly in the same direction. So we have a couple of iterations of the Harry. The version 1, we should focus on the proof of concept. And we try to get everything relatively working so we can get the funding from the government. The version 2 onward, we try to get it down to the size of the CubeSat, so 10 by 10 by 10. And by the version 3, we're able to get it inside the CubeSat quite neatly. And yeah, and this is the version that we flew on Curva 2 and Waratah Seed. So during the development, to verify that it's working, we essentially perform two kind of tests. The first one involves using Iver. So this is our GNSS simulator over here. We design a scenario. We generate a signal from out here, and it will go to the slitter here and then go to our little CubeSat over here. The second test is a little bit more exciting because that one we use our recorded RF signal from one of the. So essentially we have our receiver, we put it on the plane and we flew it over the ocean to try to capture the reflect GPS signal. We record everything and then we replayed it on the player RF2 with the discipline external clock. As you can see here, we use that to verify that we actually get this the delay Doppler map. This is what we want. So the delay Doppler map is essentially we have two axons here, delay sample and the Doppler, and because the reflect signal, so the delay between the direct signal and the reflect will have a little bit different. And what we expect to see is a very nice parabolic curve like this here. And we're able to get it when we verify using the relay signal. And finally, on August 17, 2024, we're able to launch it successfully on Space Falcon 9, as you see on the video before. It's a very exciting day for us. And so from 2024 all the way to the end of almost the end of the mid of 2025, we're able to conduct several experiments on the spacecraft. Now, the unfortunate thing is that the Waratah S-band system went down just a couple of months when it on orbit. So we essentially couldn't get any useful reflectometry data from them. And so our first mission is successful. We're able to get the navigation results from Waratah Seed 1. And they were able to verify that it can be navigated through space. Well, the second one is a bit tricky. So the question is, could we somehow use Waratah Seed 1 for the Waratah mission? And what we did is we decided to flip the satellite 180 degrees looking downward to see whether maybe we can get any reflect signal from the ocean at all. And we tried so much, we tried so hard. As you can see, it's not ideal because we have right-hand circular polarized antenna. Try to get the left-hand circular polarized signal. Yep, I know. This is almost impossible. But we have some hope. As you see here, this is what we expect, and this we actually got for a couple of months. Oh, yeah. So you see a lot of noise, sort of one tiny dot here that we assume is some kind of signal, but we couldn't verify it. So luckily, we have one very amazing student doing her thesis, and we're able to find out finally that the single profile that we have fit more into a direct signal rather than the reflect signal. We do that by she tried to particularly choose some of the. So we try to simulate what the direct signal look like at that particular point in time. We try to plot it to the sky plot, and we overlap the two sky plot for the reflect signal and the direct signal, and we got the reflect and the direct signal overlap with each other a lot. So we come to the conclusion that somehow the signal actually shift through the satellite itself into the antenna rather than we read the reflect signal. So not all the news are very bad. Incidentally, during the operation 2024-2025. We're in the middle of the war with Iran. And so the idea is if we're going to flip the satellite to look down anyway, we might get some interesting result when we go over Iran. And we did. So this is the roof of Shaman and proofing we get from Russian when we fly over Iran. Yeah, it's very exciting. So this is of my finding. And so the three main key points is how we capable of navigate through space. We able to confirm that the reflectometry signal is that from the direct signal somehow that shipped into the system rather than the reflected signal that we wanted. And we're able to verify that the GNSS jamming and spoofing are happening across Uran region. Yeah. That's all from me. Maybe if we have more time, we're gonna talk a bit more.
Just say something about this. Yeah.
Yeah, okay.
Fine. Cool.
Yeah. So there's another news that we are very exciting to announce that we are developing a new, almost finished developing a new receiver. We call it a frog mouse. So the frog mouse is a bird that Andrew really liked, and also native to one of our senior that he been moved away from us. So yeah, that's what we choose the name for. And we are at the final stage of development of this. And the key idea is it's a better hardware. So it have more powerful computer. It have 4 RF channel integrate into the circuit board, and it feature better clock system, more flexible connectivity, and more additional feature that's suitable for CubeSat, which is EMI shooting and also smaller inside. So it only takes 0.3 U CubeSat, so 3 centimeter in height. Also, it has vibration tolerant connector. And yeah, so initial test for this system is very, very good. We get into 1 meter, 80% accuracy, horizontal position accuracy for the stationary, and for the low Earth orbit simulator, able to get the 11 meter, 80% accuracy for some. But some EMI testing so that we still have a long way to go in this end, and it basically all over the place, and we need to design our net interaction of the BCB more carefully. And we also want to tell that we're very exciting that we have a lot more equipment coming to university soon. It includes some handheld coil, shaker table, anechoic chamber, thermal vacuum, and we have 2 new route stations that we're very exciting to be used in the hopefully very near future mission. Yep, so our plans for future, essentially we want to make the 3rd prototype for new receiver, hopefully the last one as well. We prepare for the testing facility for upcoming CubeSat, and we hopefully launch new receiver into space very soon. Maybe Waratah Seed too. Yeah. Oh, sorry. Thank you everyone for my very long presentation, and I'm want to personally thank everyone on the team to make it happen. And there's so many to be named, so I just take a picture of every route that involved here. Thank you so much.
Thank you very much, Dad. So what about some of the other payloads on Waratah Seed? There's the UTS Mawson Rovers payload called Matilda, which is a thermal management payload. And basically, the idea is that they're going to have 3D printed metamaterial tubes or worms, you might say, going from a hot semiconductor processor down at the bottom up through a volume to an outside region where they want to transmit the heat to. So you could just use a wire, right? Thermal conduction, but that's rather heavy and massive. You want to be able to try and maximize your heat transfer and minimize your weight. And that's why they went to a 3D printed tubular approach. And then you say, well, what could I put in my tube? I could put wax in there. Why would you put wax? The reason is because the heat that gets transmitted along can then be used to melt the wax, and takes quite a lot of energy, the latent heat of fusion, to be able to melt it. And then even after that, you can then have thermal conduction going on, convection going on. So you've got many more ways of transmitting the heat or from one place to another using this type of approach. And this is something that a number of people at UTS have been working on, including Nick Bennett, Larissa Ruofa, and also Zhen Lao. And so here are some of the results. What do we have here? We've got the temperature of the electronics here on the upper, the left-hand axis, time on the bottom axis, and then we have our standard, heat sink, has a certain profile. And with your metamaterials and your phase-changing material, aka wax, you can see that you now have a much longer time to getting up to this maximum temperature. That's what you want. You want to maximize your operating time. And then it's much, much slower to cool back down to the temperature of space in inverted commas. So this allows you to keep the temperature in an optimum regime much more easily. And they've shown that they can do this multiple times. They've got replicability. It's a really nice experiment, and showing that this type of technology really has a future. In fact, Zhen Lo and a number of us just submitted an Australian Economic Accelerator proposal, which we had an interview for earlier this week. And in that proposal, we propose doing, yes, spacecraft electronics this way, but also things like batteries in electric vehicles, which also you want to keep the temperature down low while you're charging them, for instance. So there's multiple reasons for doing this. So what about another one? Here's Deneb Space. We've got Ann Bettens over here. Got Zihao Wang in the middle, and then Shilian Bai. And this is, they've got multiple purposes, but one of them is to be able to reliably and much more efficiently point your satellite. Is this me? It's me. In the direction you want to do it. So it's another way of doing an attitude determination and control system that we'll talk about. Now, Deneb wants to also get into the space transportation business and the space manufacturing and space business, again, for which you want to be able to reorient satellites, put them together in particular ways to do particular tasks. And so here is one bit of the technology. It's EMAG, electro-permanent magnetorquer. This is one of the boards that we flew on Waratah Seed. And basically, it's a clever way of getting a magnetic field here, which you're then going to use to torque against Earth's magnetic field and then orient the spacecraft the way you want. Usually what one does is to have coils of wire, pass an electric current through them. That gives you a magnetic field. But you have to keep on putting the current through that. Wouldn't it be nice if you could just put a current through once for a short period of time, change some magnetic domains into a desired orientation, that magnetic field stays there, and it torques against Earth's magnetic field? And that's basically what Deneb's idea is, and which we have shown to work nicely in space. And this is, I find it a complicated diagram. But what it's intended to do, in fact, I'm really going to ignore it mostly, except to say that what you want is a big area here, and that corresponds to EMAG. You want to have efficient use of the volume you have available. You want to have a large torque that you're going to generate. You want to have a small amount of power giving you a large torque. And you want to be efficient at using whatever power you have. And you notice that all of the competitors lie inside this volume, inside this area, indicating that EMAG is much more efficient and effective. And so we actually use about 1% of the power of other systems, and we get about 10 times the rotational torque. That's really a very exciting way to try and do attitude determination and control systems in space. It also has got other things that are exciting because you can, for instance, just let it be there, turn it on with a particular orientation of the magnetic domains, and then that allows you to de-spin the spacecraft very efficiently. So a number of things. What about extraterrestrial power? This is a company with Peter Toth in the center here is the principal, with Gavin Conybeare at UNSW. Patrick Opel is the Waratah Seed engineer. Over here on the left, and Shelian Bai again is the Kuava engineer. And they're all about advanced solar cells, silicon solar cells for spacecraft. And so here's a picture of one of their devices. This was put onto the spacecraft. You can see a number of different solar cells, some of them treated in particular ways. Also have a radiation counter here. You might wonder why you have a radiation counter. The reason is because if you have a high energy ion coming along, it can bang into an electric current, electrical wire, and basically break it. Essentially just move atoms out of the way, reduce the amount of current that can flow through it. So we wanted to see that effect. They wanted to see that effect in their solar cells. And you can see here the vision, affordable power in space, mass manufacturing, and 10 times cheaper than current solar cells. It's worth mentioning that for Waratah Seed, the solar cells that we bought were over 100,000 Australian dollars. It was so nice to have that be $10,000. And so here are some of the results. What we have here is the current as a function of time. You can see the periodic variations here. What do you think that is?
Rotation.
Could be rotation. Turns out the timing, which you can't tell here, is about 95 minutes. So what do you think it would be? It's the orbital period. So you're going in and out of sunlight here. And you're seeing this pattern. And down here on the left is meant to be the current going into the battery. And so it's actually a demonstration that extraterrestrial power was actually able to give current and power to our spacecraft, which is, a major technological milestone for them, just showing that it worked in space. And they've actually managed to convert that into a contract with Skycraft, which some of you will know. It's an Australian satellite company that's doing aircraft communications and safety globally. And they've now got a contract for solar cells with them. What about Europa Power? Anita Ho-Bailey is the principal here. And I'm sorry, but I don't remember his name right at the moment. But she has a large group of people, and they're all about high-performance perovskite solar cells. Turns out perovskites are really neat. I'll talk about it here, just because it turns out to be an amorphous material that is really resistant to radiation damage. So if you've got amorphous powder, really all that means is you've got little blobs of material. An ion or something comes along, knocks a few out of the way. Well, where are they going to go? They're going to scatter out, come back in. So extremely resistant to radiation damage. And so here are some of their solar cells. You can see there, 9 different ones here. Sorry, 8 different ones. It's also, I didn't say this, it's a very thin film, so it's not massive at all. And it's resistant to radiation, but also the heating is the thing that allows it to heal effectively. So moving the particles around. And here's some results. Now, Anita told me that I was not allowed to talk about the scales here. A student would normally get, very low marks for presenting something like this without any scales, let alone no error bars. And this is basically the current versus voltage characteristics of sort of solar cells. And one thing that's nice is as you go down here towards high voltage and then go back the other side, going into darkness, for instance, you can see that it's almost on top of each other. So very little hysteresis. And some of you will know that in an IV curve like this, the product of current times voltage is power. So if you've got an area in between your outgoing curve and your ingoing curve, corresponds to power being lost or deposited often into your solar cell, which is probably not a good thing. So it's really quite attractive. Dandelions, I think I'm going to skip over it to say that this is biomaterials. And basically they were doing a mechanical experiment where they'd go and compress a material and then they'd let it expand and then they'd do it again and again just to see whether the expansion and compression properties change time. And they did this many times. And I will just tell you that so far, having done it for by the time I took, they gave me this, it was 6 months in orbit. They saw no difference in the results, which is really good because they want to see biomaterials which are resistant to the effects of space. So I'm just going to skip over that and I'm going to skip over myself, except to say that this is my student Quinn Musselin. This is a device he put together, obviously with help from me and others. It's a device here, and this is the electron density and debris instrument. We're wanting to know what the thermal plasma environment is. So we want to know the density and temperature. We also want to see hits on the spacecraft of bits of space debris, which we see coming out as, well, basically little, well, you can regard the dust particles as very little dinosaur killers. So you get a plume of material from the spacecraft and the dust object, the object. It's sufficiently hot because of the 7 kilometers a second or so of relative velocity, get a temperature of order 20,000 degrees Kelvin. So it's melted, it's gaseous, it's also ionized. And so you get the electrons going out first because they're light and fast. Then you see the ions. And so you see this voltage pulse that we hope to see. And actually, I'm fibbed. I'm going to show you it anyway. So this is frequency here, 10 megahertz here, time, and this is 100 minutes, so 1 orbit. And you can see with the eyes of faith, a signal here that's above 10 megahertz that varies with time a little bit. We think that's probably the electron plasma frequency, so giving us the density. And all these spikes here, we hope are debris hits on the spacecraft. We're not certain of that yet. So this is the sort of thing we hope to be investigating properly. So I didn't talk at all about spiral blue, except I shall just say that their edge computer worked in space. It did the processing that they wanted, gave the results back that were expected. So that's a positive milestone for them, but it doesn't look very exciting to you. What's our current status? Well, about, gosh, it's almost a year ago, we were declared a success by New South Wales government because we had all of the spacecraft systems commissioned and nominal. 8 of the 9 payloads were working, including the 2 main ones, Harry 3 and also Matilda. And many of the others were doing so as well. So we've now got all of our payloads teams, except perhaps one, having space heritage and their devices being TRL-8. Now gone over 18 months in orbit. We traveled about 2.3 AU. So 1 AU, of course, is the distance between the Earth and Sun. We're around about 460 kilometers in height, although Tony might correct me in detail.
I should have brought another graph. I'll do it tomorrow.
But it is of order 460 kilometers. And that means we're expecting to get of order 2 more years in orbit before we re-enter and burn up. The satellite's alive, it's pretty well. We've recovered the UHF VHF ground station. We've restored S-band communications. They basically went out in June last year, and then we had a whole series of problems with windstorms and so on with our UHF VHF ground station. But in January this year, we regained S-band communications, intermittently, admittedly, and that's because we have an attitude determination and control system. Basically, the spacecraft, we're finding at the moment we can't point it exactly where we want. And so when we're trying to get S-band communications, which is in the 1 gigahertz range, and it's got a high data downlink, we just have to wait until the spacecraft happens to be pointing within its plus or minus 45-degree cone at the ground station. And then it turns out we get data downlink. We got some GPS data last week. We got some extraterrestrial power the week before, data the week before. So we're good. We're surprisingly good at the moment. Lots of implications, and I'm not going to talk a lot, except to say that here cost about 1.8 million, including the extension of order another half year beyond what we were expected to be. Launch is only about 20% of that, so we're not determined entirely by launch. Our return on investment is greater than 10, and that's just using the increase in value of two of our companies, our startups, Deneb and Extraterrestrial Power. So huge increases in value. And so that's a great marker for New South Wales government and for SmartSat. You notice that, our first contract that we got was December 2021. We decided our last payload, which made us economically viable, in April 2023. So it's about a year and a half later. And then we were launched just a little bit over a year and a quarter later. And so it's about 1.3 years from final selection to launch. And that's the sort of cadence we're looking for in the future, 1.5, 2 years. And it's a big collaboration. It's academia, it's industry, it's government. They all worked well together, in part because we're transparent and we talk. It's amazing how often people don't talk. And these sorts of collaborations, are things that government and universities and industry should try and do more of. We got 6 startups to space and 1 university, that's UTS for the first time. UNSW had already been to space with us all. And 8 of 9 of our payloads are operational. So it's really can be a good way of getting lots of people into space and getting real value. So what's a future? One view for a future is Waratah.space. You'll notice it's similar, but not the same as Waratah Seed. Same initials, but subtly different. So try and increase, not lose all of our branding / PR status on changing names. And what we're wanting to do is to really be a pipeline to space for payloads for multiple purposes: heritage, development, so R&D, commercial operation, and then training of people. All of those things are absolutely vital, arguably, for our country. And the way to go about this, if you have a pipeline, that means something that's reliable, resilient. It happens. You can't do a one-off space mission and say, I got a pipeline. You've got to have a number in a row. And we're going for 3 in a row, once every year, once the first 2 years is gone. We expect it to be cost effective and large return on investment. We don't want to just be New South Wales. We want to be all of Australia and also internationally. And we're looking to try and develop a national capability or an infrastructure for the whole country. But it's only one path. We don't expect that everybody's going to want to come and be with Waratah.space. It's got to be part of it. And so what is it going to be? Looking at a 12U satellite, which gives us about 9U, maybe a little bit more of payloads. We're going to take the Waratah Seed and Koala bus and basically upgrade it with perhaps X-band radio, internet in space, rather than just and have many payloads on at a time. Deployable solar panels, so we have more power, have the payloads on, and we want to have much more downlink. So annual cadence set of 3 initially. And as of approximately 1 and a bit weeks ago, University of Sydney has agreed to be the lead partner and the first client. So we will get of order $1 million cash from the university, and they'll waive at least $3 million of other money in indirect costs. And we have others that are keen. Waratah Power says they want to be part of it. Extraterrestrial Power wants to sell us solar cells. We've got a number of others, including hopefully UNSW, that want to fly with us. And the timing is early 2028 that we want to go for the first one. And please tell your friends, etc., etc. We want you to become part of Waratah.space. And here are the conclusions. I think I'm just going to mostly leave those up, except to say Waratah Seed's been really a great success. We're still alive. We're still producing data for people. We're expected to go to the middle of this year with the funding we have. And maybe if we get more Waratah.space funding, we'll be able to increase that further for Waratah Seed as well. And looks like we're really globally very successful. Doesn't mean that we're the only game in town, or we should be, but seems a good model. And we've got a lot of people who've said they're interested. Whether that translates into actual signatures on pieces of paper and money is another matter entirely. And that is one of the issues with commercial life, and for that matter, government life. You've actually got to get money. And most people like to keep their money in their wallet rather than spending it. So they've got to be convinced that there's a really good investment model and really good outcomes. And I think Waratah Seed and Waratah.space is one way to give people those outcomes. So thank you all very much. And Dat and I think we're ready to answer questions if you have any. So thank you.
I think I'd take local questions in the room, because I haven't seen anything.
Scott and then Anne, yes.
Two, I think, quick questions. First of all, whereabouts is your receiving antenna? Is it at one of the universities?
Yes, both the receiving and the transmitting antennas for our UHF VHF are on top of the electrical engineering building at University of Sydney. But that's for UHF VHF. For S-band, we use Amazon ground station services, and their facility is near Dubbo.
Okay. Second question, you're getting a lot of really interesting research done on your satellite. Is there a next step where those groups can get funding to commercialize the results of their research?
So I think the answer is yes, for sure. I mean, Extraterrestrial Power already has a contract. I don't know how much it's worth, but a contract with Skycraft. So they're progressing on. In fact, Peter told me, I guess a couple of months ago, that they have a large order book. What large means, I don't really know. But he sounds very confident. Denab with Anne Bettens and Shirley Bai, for instance, I happen to be a shareholder too, have, what's the right term? Have a number of conversations going. We were offered by Space Machines that they would give us $1 million for 10% of the company. For better or worse, we didn't say yes. But it just shows some of the value there. That's Euroka. Spiral Blue, they are very successful now, not just because of Waratah Seed, of course, but they've now flown something like 8 of their payloads their edge computers in space. They're now going on to do LiDARs. So, progressing somewhere else. Dandelions has used their new capabilities and a bit of, their PR to go and work with BHP doing exactly what? I'm not allowed to tell you. Who else should I talk about? Well, I know that UNSW has lots of discussions going on with various partners around the world about using their GPS receivers on board. And then UTS, as I mentioned, Zhen Lo or Jeff Lowe has various plans to commercialize this heat transfer approach. And it's not just satellites, it's also, charging of electric vehicle batteries, for instance. So multiple ways that you can apply some of these clever technologies where you're trying to get heat away from something that you care about. So I think really, I mean, that's where our rate of return is coming from. And, it's greater than 10, and we didn't even count, the uplift in various other companies. So it's really quite exciting. Anne.
Did you speak to the fact that you had 9 payloads on a tiny little satellite and almost all of them worked? And
yeah, so I mean,
that was what seemed to have stunned a lot of people, probably why you guys won the award, because most people have just one.
Yes, I mean, yes, exactly right. We went for a very large number of payloads, carefully integrated together. We worked hard to help people become space ready. Bluntly, only one of our 9 was ready out of the box. But that's the model, because most people can't. Even though they work really hard at something, they can't produce something that is space qualified and is able to connect to your satellite bus and your software system and so on. It takes a lot of work. So that aspect of the model is really important. But I think you're exactly right. Having 8 of 9 work on orbit is, apart from, high-end NASA spacecraft and ESA spacecraft, it is very unusual. The engineers were saying, Iver, no, stop, 2 is enough, maybe 3, 4, 5, 6, Iver, no more, please. But I think it just shows the importance of being flexible, but also it's a matter of resilience, because if you only have 3 payloads on board and something goes wrong in, let's say there's radiation damage of the main microprocessor for 1 or 2 of them, suddenly you've got, your 1/3 of your payloads working. You're almost certainly going to be considered a failure. Whereas if you have 8 of 9, well, you've got a lot there, so you can lose, 3, 4, and everyone's still going to be really happy, because the ones who get into space, they can and get increased TRL, etc., they can sell that capability. So I think it's a really important aspect. And another part, which I don't think Dat and I have yet touched on, is that Coava 2 carried actually quite a number of the University of Sydney and UNSW payloads for Waratah Seed. So we also had the GPS receiver, slightly different version. We had the electropermanent magnet corker on board. We had an eddy on board. And that idea of trying to have 2 satellites for almost the price of 1, apart from the launch, is, I think, a good idea. Because, Coava 2, as Dat said, it was it got damaged by radiation approximately 1.5 months after launch. And it was so frustrating, because everything was perfect with it. The commissioning was great. Just turn on the S-band, it works. The attitude determination controls, it works. Everything just was beautiful. And then we started commissioning the payloads. And first one, the radiation counter, great. Start with some of the other ones. They took power. So the imager, advanced 1-unit hyperspectral imager took power. Some little software glitch, so stopped us getting a image that was not zeros. Same with the star tracker. And we were just coming back to change the software. upload new software on it, fix it, and suddenly the payload computer is zapped. And it's in a U-boot phase, for those of you who know and care about such things, where it boots into that, and then it's meant to take software and boot the rest of the processor, and it's stuck there. And we can see that because the power usage is consistent with the U-boot phase. We've tried rebooting it, sorts of things, but because yours truly used the last, what's it called? I'm just going to call it connector, which we could have used for a debug port. Yeah, we used the last port to connect another payload, and turns out that was an error. So you live, sometimes you die by the sword as well. But it's that resilience, I think, that's a really important way to go.
Time for 2 more questions.
On the same topic, how many payload you intended for the 12U CubeSat this time?
Well, that really depends on who puts in who pays us, bluntly. So in general, I'm envisaging that we'll probably have, 2 per U. Having said that, some systems like a LiDAR, the one that Taufik has talked to me a little bit about, the Spiral Blue, that's 3U. So maybe that would be 3U, 1 payload. But I'm envisaging that, the University of Sydney, with its 1U, I imagine that we're going to have engineering student teams doing quarter U payloads. So I'll have 4 or so there. And that's why we need to go to having an Ethernet in space type approach, so that we can more easily connect multiple payloads. So it would be 20.
Oh, wow.
And I'm not scared about it. Maybe I should be.
Leave a port for the.
We are going to have a debug port on every single one of our processes. Yes.
Quick question. So a lot of the smaller companies are doing payloads that you're putting onto Waratah. Do you find there's a bit of a talent gap in terms of satellite manufacturing that you guys do? So obviously you're quite experienced. But are there other younger engineers picking up these positions in the manufacturing side?
I think the answer is yes and no. Yes, as in we quite often have students come and do an internship of, let's say 10 weeks, a semester sort of number, and they learn many things. On the other hand, have we had the money to employ more than 2 engineers? And the answer is mostly no. And what one really wants, if one's going to, train a large number of people, is obviously to have turnover of those people, of those positions. And one of the things that is nice about having a cadence, let's say a 2-year cadence, is that you start off 1 year. After 1 year, so time 0, after 1 year, the next one is starting. Now, you can't really have the same engineers working on that. So we're going to need 2 teams of engineers. So we're going to need 4 engineers rather than 2, for instance. And I think so that having that cadence will give us more opportunity to train people. And I think it is necessary. If you look around, there are some very good companies out there. I mean, Skycraft has excellent engineers and people. There's another one I was thinking of. Iver has got a long track history now. Perhaps not quite as successful in many ways, but they're making progress and they're doing high-end things well. I don't know how big their turnover is. Ours is not big, as I mentioned, and we need it to become bigger. But that's partly because we have a very different model from groups like Space Machines, where they basically seem to get a huge number of interns in. They don't pay them anything. And then they have, a few engineers of their own that are paid. So you've got this these satellites that it's an interesting model. You know, you have a lot of people trained for relatively little money, but what's your quality control like? Maybe with AI and so on, it's a perfect way to go. I don't know. So at the moment, yeah, I think we don't have as much capability as we want, and yet we graduate, what is it, 20 space engineering students a year from the University of Sydney. Might be 10, but it's, you know, within a factor of 2. UNSW will have some, UTS, a lot of people being trained, not yet enough opportunities for them. And I think that's what we all have to work towards, where we have more trained people in companies, because not everyone's going to be at university. Some of them are in defense, etc. Much better balanced, resilient ecosystem. And that does require jobs and it requires training. I feel bad that no one online has, oh, sorry. Oh, yes, sorry.
Oh, yeah, okay, that's the problem. But thanks very much. It's great.